Welcome to qnawire.
In this problem, we're going to talk about static equilibrium. Let's suppose we have a strut and a block that's supported by this strut, and the strut itself is supported by a rope and a pivot. Okay, and here we have a wall. This is pretty much the setup of our problem in our exercise. But let me give you a brief overview of how we generally solve these types of problems. Let's say that this angle here is theta. So for an object to be in static equilibrium, we need that the sum of the forces over the object be equal to zero. That must be true. And also the sum of the torques that act on the object must be equal to zero. The first condition guarantees that the center of mass of the object won't move, and the second condition guarantees that the torque, that the object will not rotate around the pivot. Okay, so now we can go on to our problem. And before going on, we just need to remember that F, actually, that the torque, tau, is equal to F cross R, where R is the distance between the point where the force is being applied and the center of rotation. And so the magnitude of the torque can be written as F times R times the sine of theta, where theta is the angle between the force being applied and the line that connects the center of rotation to the point where the force is being applied. Okay, so now we can move on to our exercise. What we have are two setups, and in the first one, I'm going to call it A, we have the strut exactly as before, so actually I'm not even going to use the same uh, drawing. So the angle theta, we have the angle of 30 degrees. We have that the weight of the block is W, the weight of the strut is also W, and the tension on the string is T. So what I'm going to do is to draw a force diagram on the strut. So here, at this point, we have the weight force coming from the block, weight force W. At this point, we also have the tension perpendicular to the weight force. We have the weight force acting on the strut itself. It acts on the center of mass of the strut. And finally, we have the force that the pivot exerts on the strut. It points somewhere in this direction. Okay, I'm just drawing a general direction um, to the northeast. And also, I'm going to write that W, I'm going to set up a coordinate system such that the y-axis points to the north, the x-axis points to the right. So W is equal to minus W, J, T is equal to minus T, I, where W and J are the magnitudes of the forces. So what we need to do is to find both the tension, magnitude of the tension, T, and also the direction and magnitude of the force, F. And here in my drawing, it seems like the force necessarily is pointing in the direction of the strut. Since that's not true, let me just be a little clearer. Let's say that it points in a general direction. So we have two equations. The first one that I'm going to apply is the equation for the torque. So the sum of the torques is zero. Notice that the strut, if it were to rotate, it will rotate around the pivot. So the force that the pivot exerts on the strut will not be counted in the torque equation because the distance between the point where the force is applied and the center of rotation is zero. So in this angle here is 30 degrees. This means that this one is 60. And by the right hand rule, we can see that the direction of the torque coming from the tension on the rope is equal, yeah, the direction is in the z direction, given that the z direction is coming out of the screen. Okay. And I'm going to consider this direction the positive direction. The negative z direction, I'm going to consider the negative direction. So the torque coming from T is equal to T times the length of the rope. I'm going to call it L, TL times the sine of 60. The torque that is exerted by the weight force coming from the block, I'm going to call it tau W1, is equal to omega L times sine of 60. Actually, up here I wrote sine of 60, should have been sine of 30, I'm sorry. And there's a minus sign here because by the right hand rule, you can see that the torque coming from the weight force is pointing in the negative z direction. Then tau W2 coming from the weight force on the strut is equal to WL over 2, since it acts on the center of mass, times sine of 60. So the sum of the torques is TL times sine of 30 minus 3WL over 2 sine of 60, and this is equal to 0. So the L's can be cancelled out. So T is equal to 3W over 2. The sine of 60 is the square root of 3 over 2, while the sine of 30 is 1/2. So T is 3, the square root of 3W over 2. This is the magnitude of T. That's the first answer we needed. The second one is the total force of the pivot. Now notice that the sum of the forces in this case is equal to the force F that the pivot exerts plus the tension plus 2 times W, and this must be equal to 0. So the force is minus tension minus 2W. If you remember, the tension is equal to minus T in the x direction. So if we put a minus in front, that's Ti plus 2Wj. Now, using that T is the square root of 3, 3 times the square root of 3 divided by 2I plus 2j. So magnitude of the force is W times the square root of 3, actually 9 times 3 over 4 plus 4, because I'm squaring each component and then taking the square root. So this is equal to the square root of 43 over 4 times W. This is the value of the force. This is the magnitude of the force. And the angle theta will be the arctangent of the y component divided by the x component. And this is equal to 37.6 degrees. Okay, and this concludes the first item. And now we can move on to the second one, B. And the setup we have in that item is the strut right here. Then we have an angle of 45 degrees. The rope is making an angle of 30 degrees with the ground, and the block is just as before. Okay. Before doing anything else, I'm going to write again that W is minus WJ T is equal to minus the tension, the magnitude of the tension, times uh, the sine of 60 degrees, because notice that this angle here is 60. Okay. Uh, so actually, let me just be a little more clear. I'm going to write this as the cosine of 30 minus the cosine of 30 I plus cosine plus sine of 30j. Okay, so what we have to do first is to apply that the total torque is equal to 0. Notice that the angle that the rope does with the strut is equal to 15 degrees, and we can show that. I'm going to zoom in here. This is the situation. Notice that the strut, that rope makes an angle of 30 degrees with the ground. Here is an angle of 45 degrees. So this means that in order for this to be a triangle, we need that this angle be 15 degrees, so that the sum is 90. Okay. So the torque exerted by the rope is equal to the force T times the sine of 15 times L, the torque exerted by W, the force, the first force, the gravitational force on the um, block is equal to WL sine of 45, because this angle here must be 45, tau W2 is equal to WL sine of 45 divided by 2, since it's applied here. Okay, so the total torque is TL sine of 15 minus 3 WL over 2 sine of 45, and this is equal to 0. The L cancel out, and we're left with T is equal to 3 W over 2 sine of 45 divided by sine of 15, and this is equal to 4.1 W. This is the magnitude of the tension. Now I have to find the direction and magnitude of the force F. So from a 4, you can see that the force F is minus the sum of the tension plus 2W. Now the tension is minus T. I'm going to write it like this. Minus T times cosine of theta so cosine of 60 I plus sine of 60, actually it should be 30, I'm sorry. Cosine of 30 I plus sine of 30j, that's what I said before, minus 2 wj. So the minuses cancel out, and we have 4.1 w times cosine of 30i plus sine of 30j plus 2wj. So this is equal to 3.55 wi plus 2.05 wj plus 2wj, and this is equal to 3.55 wi plus 4.05 wj. So so the magnitude of the force is equal to the square root of 3.55 squared plus 4.05 squared, and this is equal to 5.39 newtons. Actually, not newton. There should be a W here. So 5.39 W. This is the magnitude, and the direction of the force, theta, is the arc tangent of 4.05 divided by 3.55, and this is equal to 48.76 degrees. And this is the conclusion of our exercise.